The splendid folds in these cliffs are in Carboniferous strata on the North Cornish coast. They were formed nearly 300 million years ago when great continental plates collided. And as they came together, they lifted up and they squeezed and buckled great piles of sediment that had accumulated in the seas that once lay between them. So these are marine sediments. The darker layers are hard shales that were once muds, and the lighter coloured layers are siltstones and sandstone. And these layers have been folded over on themselves, so that these layers here are actually upside down. And if you follow them up and round the fold, they come right way up again up there. Now, in some places, the folding's been so strong that the folds have actually been broken. And the top part of the fold has slid over, or it's been thrust over the bottom part. Well, these are pretty impressive folds, but actually they're relatively small scale because they're part of a much larger fold structure that can be followed for several miles across country. And in this program, we're going to be looking at the sorts of earth movements that happen when continental masses come together and great masses of sediment are lifted up from the sea and crumpled like this.
One of the youngest fold mountain belts formed in this way is the Alpine Himalayan belt. Some of these peaks have been pushed up to 9 kilometers high, and they contain young sedimentary rocks and fossils originally formed beneath the sea. This uplift of fold mountains is the most dramatic surface evidence of the Earth's internal dynamics. But of course, most of the continental crust of the Earth's surface isn't formed of young mountain belts. The rest is much older, and it's underlain by thick lithosphere, which is stable and rigid. And these stable blocks form about 2/3 of the continents. And in the process of continental drift, they move around the surface of the Earth without deforming. At the surface, we find these blocks as relatively low-lying, ancient Precambrian continental shields. Here's one of the largest, the Canadian Greenland Shield, shaded in dark green. Down here is the Brazilian Shield, and over here, the African and the Baltic shields. These shields continue beneath the sedimentary cover of the continental platforms, coloured light green, and these are also stable and rigid. These yellow zones are the young mountain chains and areas of recent volcanism. They're concentrated in two main zones. This one around the Pacific, and the one we're going to look at in some detail, the Alpine Himalayan belt. This mountain belt is the result of a major continental collision which started in the recent geological past. But a collision isn't a single event, it happened as a series of complex plate movements. And here is a reconstruction of what we think the plates looked like 200 million years ago. At that time, all the continents had come together to form a single supercontinent, Pangaea, leaving a massive single ocean encircling the rest of the globe. This is Tethys, a V-shaped ocean in the coastline of Pangaea, separating the parts that were to become Europe and Africa. Here are the outlines of the Americas. Down here is Australia, and most out of place of all, India. During the last 200 million years, there's been a continuous motion involving an interconnecting network of ocean ridges and transform faults, all leading towards the breakup of this supercontinent and the closure of Tethys. A rift developed between North Africa and North America as the crust was stretched and pulled apart. This rifting was accompanied by the eruption of alkali basalt lavas. The northern continents pivoted clockwise as a new ocean opened up to the west. The northern continents, Laurasia, and the southern continents, Gondwanaland, became separated. India had broken away from Gondwanaland and moved rapidly, leaving a new ocean, the Indian Ocean, to the south. By 80 million years ago, the opening of the South Atlantic was well underway, shunting Africa to the east. At the same time, Australia separated from Antarctica as a new spreading ridge developed between them. Finally, the continents collided to form the Alps and Himalayas. Tethys had closed over a period of 200 million years, but the details of this become much more clear if we trace the movements of India for just the last 100 million years of geological time. India moved northwards as seafloor spreading took place from the southeast Indian and Carlsberg ridges. Oceanic fracture zones developed to either side. As India was pushed northwards, Tethyan ocean crust was being consumed to the north, beneath Tibet. Back to about 200 million years ago, because that's the age of the oldest ocean crust. Well, so far, we've seen a fairly generalized model of the tectonic forces that resulted in the closure of Tethys and the formation of the Alps and Himalayas. Of course, in much more detail, the story is complicated. This is a geological cross-section of the Himalayas. At first sight, it looks rather complicated, but it contains several important features. The central zone is composed of deformed and thrusted sedimentary strata. Squeezed up with these sediments are remnants of ocean lithosphere, ophiolites, that became trapped. And beneath the sediments are granite plutons. Strongly deformed sedimentary strata, ophiolites, and granites are the basic geological characteristics of continental collision zones. This is a generalized cross-section through Tethys before continental collision took place. On the northern side, ocean lithosphere was being subducted back into the mantle. On top of the ocean crust was a cover of marine sediments composed of mudstones and oozes. As the two continents came together, deltas built out from the continental margins and the ocean floor sediments began to deform. They became strongly faulted and folded. Huge naps developed and ophiolites were emplaced. During and after the main collision, the entire region was heated up, firstly because of frictional heating, where rock masses have ground past each other along faults, and secondly, because many of the uppermost sedimentary layers are rich in heat-producing radioisotopes. As a result, melting takes place, and granite magmas may be generated, both within subducted ocean crust and also within the thickened continental pile. From geochemical data, it seems that these granites are associated with pre-collision subduction, whereas these are generally formed after collision has occurred. Later on, erosion occurs and the internal structure of the mountains is revealed. These sedimentary strata are intercalated in a complex fashion because of the effects of folding. As in this plasticine model, the sedimentary strata may become tightly folded, concertina fashion, producing highly contorted patterns on outcrops. These small zigzag folds are common on the surface of outcrops, and they're mirrored on the much larger scale by folds like these in the Austrian Alps. The whole process of crustal shortening across the axis of a collision belt can uplift the pile of sedimentary rocks until they slide away from the axis under gravity, producing enormous overfolded nap structures. These rocks are part of an inverted succession in the Swiss Alps, where the deformation has been so intense that older, darker rocks have slid across younger, lighter rocks. The boundary marks a major thrust plane that can be traced for miles across the mountainsides. On the Swiss-Italian border, the Matterhorn was brought from the south on the back of an enormous flat-lying thrust. And among these high peaks of the Pennine Alps, we find ophiolites, fragments of Tethyan ocean crust.
If we accept that ophiolites are fragments of oceanic lithosphere formed at fossil constructive plate margins, then two questions follow. How do the ophiolites get in place into fold mountain belts? And how can we use them to identify the sutures between colliding plates? If we take a look at the distribution of major ophiolite bodies on a global scale, then we can see that all the destructive plate boundaries and fold mountain belts are characterized by the presence of ophiolites. For example, here, around the Pacific, where the Pacific plate is being subducted beneath the advancing continents, and of course here, along the entire length of the alpine Himalayan chain. Ophiolites also mark an ancient plate suture here through Norway, Britain, and Canada and the eastern United States. To investigate just how ophiolites are emplaced onto plate margins from their original position several kilometers below sea level, we'll take a look at one particular ophiolite, the Oman ophiolite, which is crescent-shaped and lies on the extreme northeast edge of the once united Afro-Arabian plate. I've chosen this ophiolite because it's the largest in the world, it's beautifully exposed, and it shows the emplacement relationships particularly clearly. Also, an Open University research team has been working there for the past 6 years. Now, this is a NASA Landsat image of part of the Oman ophiolite about halfway down the crescent-shaped structure. These darker areas are the ophiolite itself, and this lighter area is of limestone, which the ophiolite is sitting on top of, and which in turn lies on top of Arabian crust. Within the ophiolite complex itself, we can draw across this satellite image the major geological units, which are analogous to the units in the modern oceanic lithosphere. These zones are dipping towards the east. This boundary marks the zone between the ophiolite and the underlying limestones. Limestones, mantle peridotite. Then a zone of gabbro, a zone of sheeted dikes, finally pillow lavas over here, before you come to young coastal plain sediments on the far right. We can understand the relationship of the units within the ophiolite to the underlying continental basement by looking at the complete structure in cross-section. The units within the ophiolite form a layered structure, and the ophiolite complex as a whole is lying on top of the Precambrian crystalline basement of the Afro-Arabian continent. The boundary between the ophiolites and the underlying rocks is mechanical. The ophiolite was either moved tectonically over the basement, or the basement was moved under the ophiolite, or possibly a combination of the two. To help let us decide between these two alternatives, let's examine the tectonic thrust zone in more detail. This is a cross-section of a couple of 100 meters across the thrust zone. This is the thrust itself, and the bottom 100 meters of the ophiolite are intensely sheared. Immediately beneath the ophiolite is a zone of high-grade metamorphism. At the contact here, temperatures of about 600 degrees centigrade were reached, and the metamorphic temperature decreased as you get away from the ophiolite until some 150 meters away, unmetamorphosed rocks are found. So what has this told us? It's told us that the shearing and the temperatures were probably caused by the movement of these two rock masses grinding past one another. But we haven't solved our original problem. Did the ophiolite move up and over the continental rocks, or did the continent move down under the ophiolite? So perhaps I can explain the problem better using this model. This represents a situation about 100 million years ago. Eurasia over here, with a piece of oceanic lithosphere attached to it. The Afro-Arabian plate here, with its oceanic lithosphere being subducted down a northeasterly inclined subduction zone. Now the possibilities are that part of the Tethyan oceanic lithosphere was abducted in a rapid way onto the leading edge of the continent. That would be a quick event, and it would really not produce the metamorphic effect that we see on the base of the ophiolite in the Oman. It's much more likely that what happened was that as subduction continued, metamorphism was produced at this contact zone, and the whole process stopped when the continental leading edge got stuck underneath the oceanic lithosphere. The next question, of course, arises as to what kind of oceanic crust is this? It's Tethyan ocean crust? Was it part of a large ocean, or was it part of a rather small ocean? Well, the field and geochemical evidence tells us it was something rather like this. The trace element geochemistry tells us it's oceanic crust that was formed by magma rising from the subduction zone, producing a new constructive margin, and the new ocean being formed as seafloor spreading opened up and produced new ocean crust. It took place on the isotopic evidence between 96 and 94 million years ago, and through this oceanic crust, more magma came up and produced island arc features, volcanoes punched up through the new ocean crust. So we can say that in this particular area, the ophiolite marks the precise site of subduction. And if ophiolites are fragments of oceanic lithosphere attached to continents above subduction zones, then this in turn applies that here in the Middle East, with the multiple ophiolite zones, then closure was a complex and multi-stage process.
Welcome back to Cornwall. You can see folded and thrust and even metamorphosed Carboniferous and Devonian rocks over a lot of southwest England. Cornwall and Devon are actually the eroded remnants of part of an ancient fold belt, the Hercynian fold belt. It probably was never as high or as spectacular as the Alps and Himalayas, but it was pretty extensive. This is a continental reconstruction, a pretty schematic one for about 270 million years ago. There's Greenland, Scandinavia, Europe and Britain, of course, Africa down here, and over here North America. Now I'll just draw in very approximately the limits of the Hercynian fold belt through southwest England, across France and into Eastern Europe, pretty approximately. Quite a large area of Spain and Portugal. The Hercynian belt clips part of northern Africa, and you even find Hercynian folded rocks in eastern North America, because of course the Atlantic wasn't there at that time. Well, now this is fairly, shall we say, generalized. There's a lot more detail could go into here, but you get the overall impression of a broad linear belt. And the overall impression you get is one of a general convergence of plates converging north and south. And of course, the Hercynian belt has got other features of the sorts that you've seen in the younger mountain chains. Cornwall and Devon are famous for their moors that are underlain by granite. The granites were intruded into the sediments soon after they'd been uplifted and folded. And because of their low density, they've risen high in the crust and they've been revealed by erosion. This is the Lizard Peninsula on the south coast of Cornwall. And here we can see another important feature of fold mountain belts. Well, in this outcrop, we've got rather irregular, more or less upright, alternating layers of darker and lighter colored rock. The darker colored rocks are fine-grained basalts. The lighter, rather more blotchy rocks are gabbros. The gabbros are very coarse in places with white feldspars as much as a couple of centimeters long. So these are igneous rocks. This is one of several basaltic dikes that have cut up through, have been intruded into these coarse gabbros. And this is probably part of an ophiolite sequence, a piece of oceanic crust. It would be a bit of the sheeted dike complex between the pillar lavas above and the gabbros and peridotites of the oceanic crust and mantle below. Most of the southern part of the Lizard Peninsula is formed of a rock that's used a lot for an ornamental stone because it takes such a lovely polish. Look at this. This is serpentinite, altered hydrated peridotite. This may well have been once part of the upper mantle. In other parts of the lizard, you find rocks like these. Banded, dark amphibolites, metamorphic rocks. They may not look much like it now, but these were once basaltic lavas. So down here on the lizard, we've got all the components of the standard ophiolite sequence. You don't find them in the right order, of course, because they've been broken up by faulting and thrusting. Well, here in Cornwall, we've seen folded sediments and granites and some ophiolite. And they're all part of the Hercynian fold belt that formed when continents collided something like 300 million years ago.
Well, that's taken us back to about 300 million years ago. And here you can see three major periods of Phanerozoic mountain building. Here are the Alpine and the Hercynian peaks. But piecing together the evidence of mountain building periods earlier in Earth history is much more difficult. We think there were several major periods of Precambrian mountain building, two here in the Proterozoic and two here in the Archean. A great deal of crustal activity took place even earlier in the Earth's history, but there's no direct evidence from before about 3,800 million years. Some of the oldest crust preserved contains 100-kilometre granitic rafts separated by linear fold belts called greenstones, and these may have formed by collision between small continental masses. But since that time, the rates of crustal processes must have decreased with time, as the driving force, the Earth's radioactive heat production, has decayed exponentially. We live on the thin outer skin of a vigorously active and dynamic planet, about whose internal structure, composition and evolution there are doubtless many secrets still to be discovered.